All right, this is the next virtual lecture for EAPS536. The topic today is the Walker circulation found in the Pacific Ocean. The relevant reading is, which is related to El Nino mostly, is very relevant, is provided there in Hartman and in Vallis. All right, so learning outcomes for today is to describe what the Walker circulation is and why it changes with ENSO, El Nino, La Nina. Explain the vertical structure of temperature and moisture in the tropics. Explain how temperature and moisture vary horizontally in the tropics. Explain how the Walker circulation can be understood conceptually using a two-layer, two-column model, which will hopefully make more sense in a little bit. All right, so first we're going to start with some basics about the Walker cell, or the Walker circulation. So in general, it's a circulation like many things in the tropics or with weak rotation. Air rises where it is relatively warm, which happens to be over the West Pacific warm pool. We're going to put some data to this. This is just a really nice conceptual diagram showing you the nature of this circulation, where warm water is not only, or the sea surface temperature is not only warmer in the Western Pacific Ocean, so you can see the North and South America on the right side of the diagram, and Australia in the left side of the diagram. So warm sea surface temperatures are found to the west. It's also a deeper layer of warmer water. And so the trade easterlies flow from east to west, generally in the deep tropics towards this warm region where air then rises and forms clouds. And then it moves, circulates back eastward aloft in the free troposphere and completes the circulation by descending gradually, actually under the influence of radiative cooling. So this is the basics of the Walker circulation is this zonal circulation, zonal overturning circulation. And so this is just a really nice diagram to put this circulation in context. So we've talked about the Hadley cell, which is a meridional overturning circulation. And so now we're thinking about a zonal overturning circulation, so east-west, and it's really predominant in the Pacific Ocean, over the Pacific Ocean, which is very large, and there's large sea surface temperature gradients there, as we'll talk about. Yeah, so this also shows where generally the strongest rain is, and so you can see the ITCZ is the zonal band of precipitation, but precipitation is generally the strongest over the Western Pacific, including the maritime continent, as we'll show. Okay, so just some basics here. So on the left is the actual annual mean sea surface temperature. I don't have the years on here, but probably for some climatological period. And then or you can see and then on the right is the annual mean rainfall. This is from TRMM satellite-based data from the GPCP. And so to put some real numbers on it, where we want to focus is what we call the maritime continent, and we call it that because there's lots of islands there, but it's mostly, so there's a continent there, there's Indonesia and Papua New Guinea and whatnot, but it's mostly water, so we generally call it the maritime continent. And then this pool of warmer sea surface temperatures, the reds and oranges on the left, is what we call the West Pacific warm pool, and obviously extends into the Indian Ocean as well. And you can see for precipitation, that's also where precipitation rates are maximized. So you see the strongest rains there in the Western Pacific Ocean, a pretty big blob over the equatorial regions there. So next we want to talk about, what's nice is to talk about variability in the Walker circulation, and this is tied intimately to the El Nino Southern Oscillation, or ENSO. So you might think this is a separate topic, but it was very, very intimately related. It's a really nice application of understanding the Walker circulation itself. So we're going to watch a movie about this right now.
Phenomenon kicks into life in the Pacific Ocean around the equator. It can affect weather around the world, changing the odds of floods, drought, heat waves, and cold seasons for different regions, even raising global temperatures. But what is El Nino, and how does it happen? Firstly, we need to know what's normally happening in the tropical Pacific. This vast stretch of ocean sees consistent winds, called trade winds, that blow from east to west. These winds push warm water near the surface in their direction of travel, so the warm water piles up on the western side of the ocean around Asia and Australasia. On the other side of the ocean, around South and Central America, as the warmer water gets pushed away from the coast, it's replaced by cold water which is pulled up from deeper down in the ocean, a process called upwelling. This creates a temperature difference across the tropical Pacific, with warmer water piled up in the west and cooler water in the east. Warmer water adds extra heat to the air, which causes the air to rise with more vigour, and it's this rising air that creates an area of more unsettled weather, with more cloud and rainfall. That rising air in the west sets up atmospheric circulation across this part of the world, with warm, moist air rising on one side of the ocean and cooler, drier air descending on the other. This circulation reinforces the easterly winds, so this part of the world sits in a self-perpetuating state until El Niño begins. If conditions are right, tropical Pacific weather systems, or slow changes in the ocean around the equator, can set off a chain of events which weaken or even reverse the usual trade winds. With weakened trade winds, there's less push of warm surface water to the western side of the ocean and less upwelling of cold water on the eastern side. This allows the usually colder parts of the ocean to warm, cancelling out the normal temperature difference. Because the area of warmest water moves, so does the associated wet and unsettled weather. This changes rainfall patterns over the equatorial Pacific, as well as the large-scale wind patterns. It's this change in winds which has a knock-on effect, changing temperature and rainfall in locations around.
And now La Nina.
On our website. El Niño peaks around Christmas time and lasts for several months. It can die back to neutral conditions, but sometimes reverses into La Niña. This is the flip side of the oscillation, which sees a strengthening of the normal trade winds. This pushes the warmest water to the far western part of the tropical Pacific and increases the upwelling of cold water in the east. This cooler water extends out from the coast of the Americas towards the central part of the ocean. La Niña.
Okay, so yeah, El Nino and La Nina are the sloshing of the upper Pacific Ocean west to east, and so I'm not going to cover that anymore other than to highlight again the emphasis on how the Walker circulation is influenced. And at the end of the day, it's really that air is going to, the rising part of the Walker circulation will be found over the relatively warm waters in the equatorial Pacific Ocean. Just to note, I'm not going to go through this. This is a figure just from Vallis with a slightly more ocean-centric view that I encourage you to look at in his book, but the concept's the same. Okay, and just for context, again, so this is something that occurs every 6 to 12 months as a frequency of 2 to 7 years, so it's not periodic. And then, so in the top left just shows you a map of where sea surface temperatures are often averaged in different regions, and then the Nino 3.4 is the most common one, and which is the in between Nino 3 and Nino 4. It spans both of them, and so the time series is shown in the bottom right. And so just to note, it typically peaks in November, has a specific seasonality to it. But again, if you'd like more information, I encourage you to look up more on El Nino. So here we're focused on the Walker circulation. Okay, so next we need a little bit of a primer on the temperature and moisture structure within the tropics. So how these vary. So free tropospheric, so we're going to kind of have 4 steps here. Is first to talk about the free tropospheric temperature profile in the tropics, what defines that, what the moisture profile in the tropics looks like, how does temperature vary horizontally, and distinguishing between the free troposphere and the boundary layer, and then how everything is ultimately linked pretty strongly to sea surface temperatures. Okay, so the starting point is the temperature profile in the tropics is nearly moist adiabatic. And so what that means is that the tropics are nearly neutral to saturated ascent. So what does that mean? So here's just this nice plot where on the x-axis is temperature, the y-axis is pressure. So we're looking at temperature as a function of pressure here, and the solid line is the tropical mean estimated from reanalysis data in the tropics. And then the shading is just a range, 2 sigma range, which is pretty narrow. And then the dashed line is a moist adiabat. So this is showing you how temperature varies nearly follows a moist adiabat as a function of pressure moving upwards within the troposphere. And so to highlight, so what do we mean by moist adiabat? To give you a little bit of a reminder, is we're really saying that the saturation theta E here is constant within the free troposphere. So within the saturated, if you assumed the atmosphere were saturated, you'd be saying that theta E star, so the star means saturated, is constant. So just put on here as a reminder of a simplified equation for theta E, equivalent potential temperature. The saturated version just means the moisture, the mixing ratio, you just assume is saturated. And so that's actually just a function of temperature. So it really becomes a variable that just represents temperature and how temperature varies. If you assumed theta E star is constant, you can back out how temperature varies, and that is the moist adiabatic lapse rate at a particular value of theta E. So a question though is, okay, so that's really fascinating. So what determines which moist adiabat? And so what's interesting is this specific moist adiabat plotted here is about 340 Kelvin is our value for theta E star. And so we'd like to understand where that comes from, because that's really pretty important here. So I should note, so where does that come from? And so really where it comes from is from the boundary layer. So if you imagine over the warm sea surface temperatures where air is rising, you have some boundary layer value of theta E there. And then that air rises. And ultimately, that actually sets the temperature profile of the entire tropical free troposphere. So why is that? Is what we're going to talk about in the next couple minutes here. But this is pretty remarkable and something unique to thinking about weakly rotating systems. So at the end of the day, air enters the free troposphere primarily via deep convective clouds. So really, deep convection is how the boundary layer communicates to the free troposphere. So if you think about the free troposphere as just losing energy to space, it's cooling radiatively. And so how it gets warmed, how that cooling is balanced at the end of the day is that there's a source of energy of air entering the free troposphere from below, which is from the boundary layer. And so ultimately that air comes specifically from the deeply convecting region of the atmosphere. And so in a moment. So why is it across the entire tropics? So there's still a second step here. So, and this is because tropical free tropospheric temperatures cannot vary much horizontally because the Coriolis force is weak. This is something we call the weak temperature gradient approximation that's often used. So we can actually see this. So on the left is still that temperature profile, and so now I've drawn a blue dashed line at 500 hectopascals, and on the right is now a horizontal map of the 2016 mean 500 hectopascal temperature in Kelvin. And so this is something you guys did in your homework as well. As you'll notice, between about 30 north and 30 south in the tropics, so we're here in the middle of the free troposphere, temperatures are nearly uniform horizontally. So again, And so why is this? Is that physically, as we talked about in this class, gravity waves, especially Kelvin waves, which are pretty large scale and very fast, move all the way around the equator in a matter of a couple of days. These waves move fast and rapidly smooth out horizontal pressure gradients, and thus temperature gradients too via hydrostatic balance. So you end up with, again, what we call the weak temperature gradient assumption in the tropics, which is that temperatures just can't vary horizontally too much when you don't have rotation or a Coriolis force to balance those pressure gradient forces. Okay, so we talked about temperature. Now, what about moisture? And so you'll find as air in the tropics is relatively moist in the boundary layer, and it's actually driest in the middle of the free troposphere. And so what's shown here at the top is a map of the 500 hectopascal relative humidity. This is an annual mean. This is actually a figure taken directly from a paper shown in the bottom left corner, which is a really great paper. I highly recommend it. Where you can see variations in moisture, and so we're going to come back to that. But so the bottom panels, and I'm just going to talk about really the bottom left panel, and you can look at the bottom middle panel as well. You can ignore the bottom right panel, are vertical profiles of the annual mean relative humidity in the tropics from reanalysis as a function of height in the bottom left and pressure in the bottom center. This was from 2013. So what you'll notice is, so there's two curves here. So one, the solid line corresponds to the entire tropics. And then, let's see. Oh, excuse me. Sorry. Solid corresponds to the warm pool region. So averaged in that black box, that black rectangle in the top plot. The Indo-Pacific warm pool, and then the dashed line is the entire tropical domain, excuse me. So you can see that the entire tropical domain gets down to a minimum relative humidity of something like 35% at a height of maybe 7 kilometers, which corresponds to about 400 millibars if you look across the two plots. And then over that moist region, where that deeply convecting region, it's quite a bit moister. So this is largely due to things like detrainment of water from convection. So it's quite a bit moister. But again, over the entire tropics, either way, there's a minimum, roughly the same altitude and the same pressure in the middle of the free troposphere. And then the boundary layer itself is quite moist. So here the relative humidity is around 80% and actually doesn't vary too much between the moist region and the entire tropical mean. So you have a moist boundary layer and a drier free troposphere. Okay, so that gives you a sense of the structure, both vertically and horizontally, in moisture and in temperature. And so now we're going to connect this back to this idea of our conserved variables. So we're going to talk about, so boundary layer theta E, and we're going to start to transition to moist static energy, which is very similar. We'll call that H, is strongly controlled by sea surface temperatures. So it's shown here. So why is that? So it's shown here on the left is a plot of the difference in temperature between the sea surface and the air just overlying the sea surface. This is from reanalysis data from 1981 to 2010 mean. And so what you'll see is these colors are all, it's kind of messy, but these colors are all in a range of about 1 to 2 Kelvin. So which says that the 2-meter air temperature, so the air just overlying the surface in the tropics, is only a little bit cooler than the sea surface temperature. So they're very, very similar, no matter where you go, whether it's warm or cold sea surface temperatures. So on the right is the 2-meter relative humidity for the same time period, the average relative humidity. And so what you'll notice from the colors is that the 2-meter relative humidity is about 80%, and the key thing is it's remarkably constant over the global oceans. Over land, things are very different, but over the oceans, this really varies pretty minimally in space. It's really remarkably constant, and even expected to remain relatively constant going into the future. So, so that's nice. So what does that mean? So we can flip this into the more relevant variables. So that means the left now just shows the 2-meter temperature, which, if you'll notice, looks a lot like the 2-meter, or it looks a lot like the sea surface temperature distribution. So we'll just say the exact same thing again as the 2-meter temperature. The boundary layer air temperature is only slightly cooler than the sea surface temperature at the bottom of the boundary layer, that is. And then on the right now shows 2 meter specific humidity, QV, so in grams per kilogram. And you'll notice this also has a distribution that looks awfully similar to the sea surface temperature distribution. And that's really because, again, we've said the relative humidity is nearly constant in space in the tropics. And so what that means, if you have constant relative humidity, then if temperatures are following the sea surface temperatures, then your moisture, your water vapor mass is also going to end up following that, specifically according to Clausius-Clapeyron. But the patterns will look very similar. So the key thing in the end then is getting back to theta E, or to moist static energy, which H, both shown in the bottom right. Is so at the end of the day then, temperature and moisture are what you care about for defining these moist thermodynamic variables. So within the boundary layer, theta E and H then are also going to be very strongly controlled by sea surface temperatures, since temperature and moisture themselves are as well. Okay, and just one thing to really highlight here is that the weak temperature gradient approximation, which we mentioned about the free troposphere, it's hard to sustain horizontal temperature gradients in the free troposphere. That's not true in the boundary layer. That does not apply in the boundary layer in the tropics. And so the reasons for that are relatively simple. And so actually maybe I'll put that up first. So there's really large heat fluxes from the surface to the boundary layer. So there's large heat sources or energy sources within the boundary layer. And so just shown on the left here is upward. This is just to kind of give you some context. The upward sensible heat fluxes from the surface to the overlying air in the tropics is something like 0 to 30 watts per meter squared. So this is relatively small, again, because the temperatures can't change too much. But the idea is if the temperatures of the air, the temperature of the air is very similar to the sea surface temperature. So if you imagined a case where the air temperature was much cooler than the sea surface temperature, then the surface heat fluxes would be much larger because that temperature difference is much bigger. And then on the right is showing the upward latent heat fluxes from the surface in watts per meter squared, which ranges from 20 to 200 watts per meter squared. So there's a lot of latent heat fluxes also being input. I should note, I suppose, that this doesn't directly influence the boundary layer temperature, just the moisture. So in general, the temperature and moisture can vary significantly horizontally within the boundary layer. So moisture can also vary significantly in the free troposphere. Anyways, just to note as well, surface friction technically slows horizontal motions in the boundary layer as well. So it's harder to mix out those horizontal gradients in temperature. So just a quick note there. Okay, so just to summarize, the behavior of the tropical atmosphere is really, in general, is very strongly controlled by the sea surface temperature distribution. And we technically figured that this was also implicit in the Hadley cell work we've done before, and now, and even to some extent in the monsoon lecture before, and now here we're talking about it, and more generally as in the Walker cell. So the sea surface temperatures generally control where convection occurs, and convection controls the communication from the boundary layer to the free troposphere, and then the free troposphere can't vary, the temperatures cannot vary much horizontally. So there's a lot of kind of simplifying assumptions we can make when we think about the tropical atmosphere, which is pretty remarkable. We're going to talk about that. Okay, so we're going to talk really a very basic intro and conceptual level understanding of a physical model for the Walker circulation. And here I'm going to emphasize that when we talk about the Walker circulation, we're really thinking about any system with variable sea surface temperatures and weak rotation. So it's a very general case, and it's something that you effectively created in your tank labs about looking at the no and weak rotation cases that you generally get thermally direct overturning circulations where fluid rises where it is relatively warm. And so this work is going to come from a recent paper by Carey Emanuel last year in JAZ called Inferences from Simple Models of Slow Convectively Coupled Processes. This is an extensive and very deep paper that synthesizes actually a lot of understanding of different topics within tropical atmospheric dynamics. and it's pretty remarkable. And so I'm just going to touch on a couple of key points here. And so again, I've put the abstract here. So I'll just read, I highlighted a couple things. This is a framework for conceptual understanding of slow, convectively coupled disturbances. And there's a few different things listed here. I've highlighted the Walker-like circulation, which is what we'll talk about here. And then the key thing to highlight is this understanding comes from 4 key approximations that are made. The first is called boundary layer energy quasi-equilibrium, which we will talk about, and that's the one thing I'm going to highlight here. That's really quantitative. And then conservation of free tropospheric moist and dry static energies, and the weak temperature gradient approximation. So let me just talk a little bit about thinking about Walker circulation physically. So this is a figure, a nice conceptual diagram from Carey Emanuel 2019. So what I want to highlight here is, so first on the left is this nice diagram, and you can think of this again as analogous to that diagram of the Walker circulation before. You have warmer, so there's a boundary layer at the bottom where those colors are noting that it's warmer and there's higher energy in the boundary layer on the left side of the diagram, and then air rises in convective clouds over that warm region. And then it moves outward and then subsides over a broader region where there's clear sky subsidence due to radiative cooling. So you have what we call radiative subsidence balance in the clear sky free troposphere. Air is cooling, and so it's losing theta E, or its potential temperature is decreasing, and so it subsides in order to or I guess I should say its temperature is decreasing, and so it subsides in order to increase its pressure and therefore warm adiabatically. And so this is how the heat balance applies in that region. So the W sub E is a subsidence rate, which is generally very slow. It's usually something like a few millimeters per second in the current climate free troposphere. Okay, so that's on the left, and on the right here are these profiles of moist static energy is the one I'm really going to focus on, and a couple of moist static energy variables there. So you'll notice, so the solid line shows the actual profile, characteristic profile of moist static energy in the tropical atmosphere. So you have a boundary layer at the bottom with constant moist static energy in the boundary layer, and then it decreases as you move into the free troposphere, and there's this minimum, and then it increases again thereafter. So I've already highlighted here in red, there's this dashed line corresponds to the saturation moist static energy. And so this, you'll notice, is a straight line up and down. So it's constant saturation moist static energy, which just implies a constant, basically a moist adiabatic lapse rate. And it's specifically, so a moist adiabatic lapse rate in the free troposphere. And so again, why is that? Is H star you write in this way, and so what happens is the moisture variable now is saturated, and so it's really just depends on temperature, technically, and pressure as well. So it's a temperature-like variable. And then in the boundary layer, you'll notice that H star has to equal the boundary layer moist static energy. So the saturated free tropospheric moist static energy is equal to the boundary layer moist static energy, something we call convective neutrality, essentially. And going back to what we had said before in the context of theta E. And then the other one to highlight here is H sub m, which is a minimum, or like a free tropospheric value of moist static energy that's smaller than the boundary layer value. So it's HM is less than HBL. And this is really because it's drier. So the temperature profile is generally moist adiabatic through the entire troposphere. But as we noted, the free troposphere is drier. And so this is generally, this deficit in moist static energy is associated with drier air there. Okay, so thermodynamically, again, this is really no different from the Hadley overturning cell in that air rises where it is warmer and moister, and it sinks where it is cooler and drier. And this is pretty general for any weakly rotating system, as you found in the tank lab. The key dynamical difference is that since the Walker circulation is zonal, we don't have to worry about changes in angular momentum or angular momentum conservation, as we've talked about for the Hadley cell and for the monsoon as well. So as a result, you can really think of the Walker cell as being largely driven thermodynamically, which is to say by zonal variations in moist static energy and specifically in the boundary layer. So that's what those colors, the blues and reds at the bottom of the schematic are trying to depict. Okay, so what we can do is actually produce, I want to introduce you to just a really simple conceptual, kind of the simplest possible conceptual way of thinking about the Walker circulation and applying some of these approximations and assumptions that we can in the tropical atmosphere. So we call this a two-layer, two-column model for the Walker circulation. So we have on the left is a column overlying warmer sea surface temperatures, and on the right is a column overlying cooler sea surface temperatures. And then I've separated these into two layers. You have a boundary layer and a free tropospheric layer, and each of these have some value of moist static energy H. And so in the free troposphere, we think about, or actually, so we'll walk you through this for a moment. So in the free troposphere, the saturation moist static energy has to be equal to each other. So we'll come back to this again in a second. And just to note, we can think of the sea surface as, in some sense, like an infinite well of quote unquote air that is saturated at the sea surface temperature. So it's a way of thinking about it using the same variables as with the air. So this H sub 0 indicates the moist static energy, assuming you are at the sea surface temperature and you are saturated at the sea surface temperature. So those are the sensible and latent heat terms on the right side there. Okay, so conceptually, we can actually think of this model in two regimes. So one is a weak circulation case, where you have deep convection in both columns. So let's say you have a temperature difference. The warmer sea surface temperature is a little bit warmer than the cooler sea surface temperature. And so you end up with this general overturning circulation, as you'd expect air to rise in the warmer column. So we can walk through these. There's some key assumptions here we can make. So first is that the free tropospheric moist static energy, or saturated moist static energy, H star FT, has to equal the boundary layer moist static energy. And so the free tropospheric lapse rate is set by the warmest value of moist static energy in the boundary layer, which is going to occur over the warmest sea surface temperatures. So this is actually just from and this will be true in both free tropospheric boxes. So this is weak temperature gradient approximation, which basically says wherever the temperatures are warmest, you're going to have gravity waves propagate from that warm region outwards into the cooler regions. So second is that let's see here. Oh yeah, right. So then second is that the cold box boundary layer moist static energy also has to equal the free tropospheric saturated moist static energy in its column. So the cold column is also deeply convecting here. And so the boundary layer, so HB comma C, has to match the free tropospheric value. So when you put these two together, it says that the boundary layer moist static energy values have to be the same in both the warm and the cold columns. So you end up with HB comma W in both boxes. So the moist static energy in the boundary layer must also be the same in both columns. So it's crazy. So at the end of the day, both columns are actually in the atmosphere are actually the same. They're going to have the same profiles of moist static energy in the boundary layer and saturated moist static energy in the free troposphere. So in this case, deeper convection is weaker in the cold column, but it's not totally shut off. And this is because the atmosphere in the cold box is a bit more stable relative to the colder ocean surface. But it's not stable enough to actually shut off deep convection in that box. Okay, so we can contrast that with the second regime, which is where if you have a sufficiently strong circulation, that deep convection will only occur in the warm column, and this overturning circulation will suppress it in the cold column. So in the simplest understanding of this is that this will occur if the SST gradient is sufficiently strong between the warm and the cold box, or over some distance here. Here we're really simplifying things. So SST difference between these boxes, if you will. And so in this case, now you can see we no longer have that tall cloud in the cold column on the right, but instead you just have these shallow cumulus clouds in this case. So, and really the key difference here now, so you can imagine the blue arrow as being a little bit stronger, strong enough to prevent updrafts, convective updrafts from occurring. The key difference here now mathematically is what this does is that the boundary layer moist static energy in the cold column now can vary independently. So when deep convection is shut off, the boundary layer really can no longer communicate with the free troposphere. So in this case, in the cold column, it's that the boundary layer is can no longer feel the saturated moist static energy of the free troposphere. And so this is in some sense more like the real Walker cell over the modern day Pacific Ocean, is that most of the deep convection occurs over the West Pacific warm pool, and there's generally a lot of shallow convection over the rest of the Pacific Ocean, including the far eastern Pacific Ocean. So that's an oversimplification. And so, but still a way to think about this is that there's, but generally a way to think about this. So I'll emphasize that simplest understanding at the top is an oversimplification as well. So, but that's probably the most straightforward conceptual way to think about this. Okay, so can we model the transition between the two regimes, or can we really understand this kind of more generally and quantitatively? And so, so what I'd like to do is to introduce one really important concept, and then I'm really not going to go through all of this in the paper. There's a tremendous amount in here, as I'll mention again in a moment. We want to go back to our original diagram of this conceptual level understanding. And so one of the central approximations that we mentioned that they make in this paper, and that's really kind of a cornerstone approximation in the field of tropical meteorology in general, comes from thinking about what sets the boundary layer moist static energy. So if everything comes down to boundary layer moist static energy in terms of where the air is rising and sinking, we have to think about, we want to think about a budget equation for the boundary layer moist static energy. And so that's this equation shown here. This is equation 2 from the paper, and it's just a budget equation. But I'm not going to go through that here, but the information is there. So it's an equation for the tendency on the left side. That D out front is a boundary layer depth. So the tendency, local tendency plus the advection is equal to sources and sinks on the right. And so what you can do is take this equation and assume a steady balance, which is something called boundary layer quasi-equilibrium. So quasi-equilibrium just means approximately steady state. And so this is a really important concept and an assumption in tropical meteorology, as I mentioned, which is to say, so you're assuming a steady state, so you're ignoring the local tendency, DHB dt, and you're also ignoring advection, which may not necessarily be a good assumption, but horizontal advection is being ignored. And then on the right-hand side, we're just keeping those first two terms. So we're essentially ignoring radiative cooling in the boundary layer. And so what is this boundary layer quasi-equilibrium? And I really just want to introduce this concept to you. So you're assuming that the moist static energy of the boundary layer in any particular location is assumed to be steady. And its value is set by a balance between, so there's two terms on the right-hand side here. So we have a source, which is surface heat fluxes, which is latent and sensible heat. So there's almost always upward heat fluxes, as we showed before, from the surface to the overlying air. So that generally is enhancing the moist static energy of that air. And then that is going to be balanced by a sink of moist static energy, which is the downward advection of lower moist static energy air from the free troposphere. And so you can see that, remember that there's a deficit of moist static energy in the free troposphere. And so that lower H air is advected downward by both convective downdraft, so that's M sub D, which is a mass flux, downdraft mass flux, as well as the radiative subsidence velocity, WE. And then HB minus HM is the difference, the moist static energy difference between the boundary layer and the free troposphere in the simplified assumption. So this is just a really important concept, and I wanted to introduce it just to make it clear, so you've heard this term and have some sense of what it means, because it's a pretty complicated sounding concept. So you can do all sorts of remarkable analytical solutions for this problem and other related problems. And to do that, you're going to have to go to the paper. So I'm hoping this gives you at least a little bit of an introduction to what's in the paper, though I won't lie, it's got quite a lot going on, but it's also pretty remarkable for understanding all sorts of things in the tropical atmosphere. So it's really too much for this class, unfortunately, but maybe in a future class focused specifically on tropical dynamics, we would spend a lot of time on it. So please go check out the paper if you're interested for more information and delving into the math and physics much more deeply. All right, go to Blackboard to answer a few questions about this topic.